This is Bob presenting on SML. This time, we're looking at a very sparse data of prostate cancer with 500 features and 79 observations. If you look at that K ratio with a 0.158, which is quite low than the expected range of 10 to 5. So looking at the data, it has observations that looked normalized between of around 0.20. So no blanks were found. Looking at the dependent variable, classes of 0 and 1. And as we look into this data, we've already seen that there is a problem. It is too sparse, and most of our learning algorithms may have problems. So distribution of the y variable, you can see it's well distributed, +7 and 42, which is rather good. We don't expect biasness. Here's the plot. And we use crucial statistics to look at importance of this variable so that you can pick maybe only 9 or 10. In this case, I used 9 that contribute or are more significant to the predicted, to the dependent variable y. So in this case, chose those 9 and plotted H plots to see how feature importance looks like for 500 features. So you can see we have a few of them at the peak end. And the bad ones are also not that bad. So box plots to visualize the top 9 predictors. You can see their means are well distributed and they are not at the same level. So this is good. And just to look at a classification tree of the 9. So you can see I had these X to 290. And out of the 9 variables, only 3 were quite significant in building a tree. And I had 4 leaf nodes. So from the terminal nodes, you can see the equations. And comparing the box plots of the weakest variables using the critical statistics. These are the variables with the weakest estimation. So here are the weakest predictors, and you can see their means are almost on the same line. So visualizing these correlation matrix, you can see we have a lot of dependencies. These are the 500 features, and the blue are highly correlated, positively correlated, up to 0.8, which is really bad. And the dark red, they're also not good. And the white regions is quite small here. So this means a lot of these biological features are always depending on each other and related. So one main thing that we are expecting here is our models are going to have problems, and we don't expect them to have high accuracies. So just a snippet of this. For the first time, I did a training with the whole data, giving this, trying to see how are KNNs with different Ks working and how are trees with different complexity features looking like. So I did training for K1NN, 7NN, and 9NN. As we know in SML, 1NN always seem to overlearn because it will have a very high variance by just mastering the data and not learning the data. And In terms of CP, the complexity of these trees, we expect CP0 to tolerate a lot of errors and just master the data and don't not learn the data in the first case where we are training the data. We are training using the whole data set. So as we expected, you can see 1NN learned everything and is like mastered all the data. And at the same time, for the trees, tree with CP0 also got the highest out of the trees. So an ROC curve from that data set is looking at this. And what if now we try to prune these trees? You can see that for CP0, it's taking more features because it is doing less penalization on features that are having high errors. So that's why it's even having 4 leaf nodes. And the others that are trying to penalize errors are having 3 leaf nodes. So one of the key things you can do here is hold out or do cross validation. In this case, let's look at how holdout worked with 100 training iterations. We're doing holdout and keeping a portion of the data for testing so that we can see how they behave, different NNs behave and different CPs behave when they are exposed to a data that they didn't see during training. So as we can expect, from high accuracies now to the highest errors. 1NN having the highest error in the trees, and tree with CP0 having the highest error of 42. So this means the model with the highest accuracy here was just a 60% accuracy. So comparing to visualize the statistics, you can see 0.4, 1NN having the highest error rate, and in terms of variance, you can see it's having the highest variance, with the tree CP0 also leading the trees. And one takeaway we can take from here is performance, or how KNN works. Increasing the trees, increasing the number of K reduces variance. Increasing the number of K reduces the variance, increasing the bias. And at the same time, increases variance and reduces bias. And performance always doesn't guarantee that the model will work good when exposed to external data. So this means that having one NN is always having high variance, and as much as it may perform well, this is just due to overfitting and mastering the data, not learning the data. So this is one of the main takeaways, and looking at how you can manage sparse data. That is one of the main things came out with from this assignment. Thank you.